Hello, Algebra 1 students. Today we're going to look at the effect of changing the slope and the y-intercept in word problems. Okay, so after today you'll be able to use the graph of linear functions to solve real-life problems and see how changing the slope and changing the intercepts affect the problems. Okay, so as we know, we could use the linear function to represent many different real-life scenarios, and in our formula y equal mx plus b, we know that the m represents the slope, and we also know that the slope in real life, it represents the rate of change, okay? And the y-intercept, which is your letter b in the formula y equals mx plus b, is it represents the starting point or the initial value of your function. Okay, so let us look at our first example, changing slope. So in this example, I have a problem situation that says to get from one floor to another at a library, you can take either the stairs or the escalator. You can climb the stairs at a rate of 1.75 feet per second, and the escalator rises at a rate of 2 feet per second. So it's slightly higher or faster. You have to travel a vertical distance of 28 feet. Okay, that means that the height of the between the two floors is 28 feet. Okay, the equations model the vertical distance d in feet you have left to travel after r seconds. So first we are going to write these two equations for the two scenarios. Okay. So the two equations I have, one is for the stairs and the other is for the escalators. We know we start at 28 feet and the slope is changing by negative 1.75 times t, which represents our time. Okay, and d represents the distance. So as we travel, as time goes by, as the seconds are ticking, we are getting closer and closer and closer to our destination. Okay, and same thing for the escalator, is d equals to negative 2 because the slope is 2 feet per second, and times t plus 28. Okay, so the first thing I'm going to do with these two equations in order to interpret the slope and how changing it affects my problem, I must graph these two lines. Okay, and when I graph these lines, I really don't want to pay attention to all the negative values. Okay, because we're talking about distance and time, so we're going to have real positive values. Okay, so I'm really gonna use just gonna use my first quadrant of my graph. So I went ahead and put some scales in there. Okay, the x-axis is time in seconds, and the y-axis is the distance in feet. And the questions in this problem is, if you were to take the stairs instead, or the escalator instead, I'm sorry, how much would you save? Okay, so the question, how much time you save if taking the escalator instead of the stairs? Okay, so because the escalator is going to be faster. Okay, so I am going to graph these two functions. And when I graph them, and you can put these into your graphing calculators and get the lines yourself. But when I graph them, I see that the stairs function intersects the x-axis at 16, which means that if I take the stairs, I would get from one floor to the next by walking in 16 seconds. Okay, and the escalator function gave me a graph that intersects the x-axis, or t in our case, at 14. That means if I take the escalator, I will reach the other floor in 14 seconds. Okay, so the stairs, I would arrive in 16 seconds, and the escalator, I would arrive in 14 seconds. So the question is, how much time am I going to save? Well, if you would subtract 16 minus 14, you would get 2 seconds. Now I wonder though, what if someone decides to change the speed of this escalator to make it go faster? Okay, we have a new line that represents the new speed, or even that, or even that, okay? How would we compare the time that we save? Well, it's quite easy if you look at the x-intercept. So here we are taking the stairs that will arrive there at in 16 seconds. If we take the first new high-speed escalator, we can see that we save 6 seconds, okay? The difference between the x-intercepts, okay? If we crank it up even faster, then you can see we are going to save 8 seconds. Now, if we crank it up super fast, we would save um, uh, 14 seconds. Now, this is not the ideal scenario because as you can see how steep that is, it means that I am able to travel at 28 feet on this escalator where I stand with no seatbelt, and I would get to my destination in 2 seconds. That speed, it's probably considered highly dangerous. So this scenario would not be ideal for us. Now, maybe 8 seconds and 10 seconds are okay. So as you can see, when you are changing the slope of the line, you are virtually changing the x-intercept of that line, okay? So being able to do this and draw the lines allow us to see which scenario is ideal and which changes would be acceptable. So when you are changing the slope of a line, you are changing the x-intercept of that line according to our example here, okay? Because we started out with the same y-intercept. So of course the y-intercept is not going to change. But if your slope of your line is changing, then you are looking at your vertical, horizontal changes in your values. So now let us look at another example. In this problem situation, we have a company produce two 30-second commercials, one for $300,000 and the second for $400,000. Each airing of either commercial on a particular station costs $150,000. The cost C in thousands of dollars to produce the first commercial and air it n times is given by the equation C equals 150n plus 300. The cost to produce the second and air it n times is given by the equation C equals 150 times n plus 400. So we can see these two equations are almost the same. Okay, the rate is changing at the same time, at the same rate, but the starting cost of one is more than the other. So the question is, what is the difference between the cost to produce each commercial and air it 2 times? Okay. Well, again, let's see if we can graph the function, okay? So I'm going to draw my graph here. The x-axis, which is n, is the number that the number of times that the commercial gets aired. And of course, the cost axis is going to be the total cost that is going to cost each commercial, okay? You notice here I had to put a little break in my graph because I couldn't fit all of those values down there. So let's just say that we started out at $200,000 here, okay? So because the cost is in thousand, all I have to do is put 200. And then 300, 400, 500, 600. You know what? Let me change this the scaling a little bit. So I changed the scaling to make the values go a little closer so that I can accommodate more numbers on this axis. So the next thing we're going to do is we're going to try to graph both of these lines. So I went ahead and graphed both of these lines. And as you can see, if you put this into your graphing calculators, you will get these two parallel lines. But remember, in order to see your lines, you have to fix your the window on your graphing calculators to 200, 300, and accommodate all of those values, okay, on your y-axis. So anyway, the reason these are parallel lines because the slopes are the same, right? We know that the slope on this one is the same as that one. That means though. no matter how many times each commercial gets aired, the change in the cost for each commercial does not change, okay? It's gonna stay the same. So the difference between the cost of these commercials will stay the same. So let's see what is the difference between the cost to produce the commercial and air it, say, 2 times, okay? So we're going to find, we're gonna look at the number 2 here, because that's the question. How much it costs to air 2 times. So we can see that the first commercial will get air. If it gets air 2 times, it's going to cost them, say, $600,000, right? Okay, and then the second one is going to cost them, the second one's going to cost them $700,000. So we're looking at these points right here, okay? So the first one cost them 600, the second one cost them 700. So we simply subtract and we would get the difference. So here I went ahead and did the subtraction, and I get 100,000. So as you can see here, it even if the question asks for the whether the commercial it's air 2 times or 4 times or 6 times or 10 times, you will see that the difference in the cost is it's going to remain 100,000, okay? Because that's the distance between these 2 points right here. Okay, so this is the horizontal, I'm sorry, the vertical difference between the points, okay? So remember when we did the change in slope, we'll look at the difference in the horizontal distance, okay? So we look at the difference between these lines right here. That's the x-axis. But when we have changes in the y-intercept, we look at the difference in the y values, okay? So that is the main thing to remember. Changes in slope, look at the difference in the x values. Changes in y-intercept, look at the difference in the y values. And this concludes our lessons. When you come to class, we get to do more activities with regards to these kind of real-world problems. So for now, I hope you enjoy the video, and thank you for watching.